Good morning, everybody. Good morning. It's so lovely to see you in the room. I was wondering how many people would be here after last night. I hope you all had a good time last night, or perhaps I'm talking to those who were sensible and went to bed early, and those who did have a very good time aren't here yet. Anyway, we are going to have a wonderful time today on day 2 of Space Resources Week. Of course, you can talk about it on Twitter, on LinkedIn, sorry, X, not Twitter anymore. Anyway, let's call it LinkedIn. That might be the best place to put information. Hashtag SpaceResWeek24. Welcome to those joining us online. It's great to have you with us once more. It was wonderful to have your presence yesterday. As with yesterday, with all of the sessions, you can just jump into the session and you can ask any questions in the chat. You will have already seen that some of the questions are answered by other people in the room in the chat as well, so it's a valuable piece of information as well. As with the course of this week, the theme is shaping global priorities and coordinating efforts to advance space resource utilization towards cleaner space activities beyond exploration. We have another parallel session tomorrow. Today, we have a lot of people flip-flopping between this room and the UNOSA expert meeting that's happening also in this building. Congratulations to everybody who showed their posters last night. It was really wonderful. And as always, thank you once more to the sponsors of this event, which make us all have a lovely time, and they really, really help lift the event year on year. Now, it's my great pleasure to hand over to Vibha Levin Prabhu from ESRIC, and she is going to host the first session this morning. We have fabulous speakers, and it's ISRU Surface Operations Part 1. So over to Vibha.
Thank you, Lisa. Thank you so much for that kind introduction. Good morning, one and all, and a very warm welcome to the second day of the 6th edition of Space Resources Week in this beautiful country of Luxembourg. Before we begin, I would like to kindly remind our presenters that you have 12 minutes time slot for your talk, which will be followed by around 3 minutes of Q&A session. So on an average total, you have 15 minutes to be on stage. I would request you to kindly stick to your schedule so that we can have all the presentations and meaningful discussions. To the audience, I encourage everyone to engage actively during the Q&A session. Let's make this an enriching experience for all of us by fostering dialogue and exchanging insights. There'll be a microphone in the room, so you can always stand up, ask your question, introduce yourself. So, in this session, we would listen to our excellent speakers discussing the first part of the ISRU value chain and dwell deeper into lunar regolith characterization, beneficiation, handling, transportation, and excavation. Without further ado, let's kick off our session. Our first presenter for today is Taeheon Kim from the Norwegian Geotechnical Institute, who would be talking to us about geotechnical characterization of the lunar regolith, a call for standardization. Welcome, Taeheon.
Hello. Yes. So my name is Taeheon Kim. I'm from the Norwegian Geotechnical Institute. So for those, some of you know us, but for those of you who don't know us, I will give a brief introduction of who we are, what we do, and then I'm going to introduce you a concept called the geotechnical ground model. Basically, that's what we do in our company, and then we will extend that, our practice, which we do on Earth, to the lunar surface, and then I'll give you some examples of knowledge gaps we have in terms of geotechnical engineering, and then end the presentation with a summary. So who we call ourselves the leading global research and consulting center for engineering geotechnics, geology, and geophysics. We are a non-profit organization. We don't make we call ourselves non-profit organization, and we are leaning more towards research, although we do some consultancy work. So what we do is we try to develop innovative methodologies when it comes to geotechnical engineering in the laboratory, numerical analysis, site investigation, anything that's related to geology, geotech, it's within our radar. I would like to introduce this very interesting thing called Norwegian geotest sites. So normally when you contact all these different competitors, they usually have laboratory, they do site investigation, all those things. But we have a very special thing that we have consortium within Norway. So we have this 5 different sites where we can test the ground itself. So we're not extracting material and testing in the laboratory, but we're actually going to the site and testing the entire ground. And then when you look up there, that's a part called Svalbard, which is quite up north. There's a permafrost region where basically the ground is always frozen all year round. So I just mentioned that because I think some of you might be interested, since there's water on the moon. When it comes to moons, lunar geotechnics, we have many projects. So one of them are what I'm showing you here. It's a discrete element analysis. So we model the particle shape. That particle shape is not from lunar simulants, but it's actually a particle from Apollo mission 14, if I remember correctly. We model that in a computer simulation and basically do a digital twin to kind of impose various environmental conditions such as gravity, temperature, vacuum, etc. Those things that are very hard to simulate on Earth conditions. So that's one of the examples where we measure the angle of repose of those simulated particles, and you can see it is affected by gravity. So this is one of the projects we've done. And so in NGI, we do laboratory work, we do site investigation, we do geophysics, we do all this kind of reconnaissance, but those work are not separate individual projects. In the end, we integrate all that information and construct a 3D reconstruction of the subsurface condition for engineering design, and we call that the geotechnical ground model. What it does is it captures all the behavior of the rock or the soil that we cannot see underground. And then it's basically a complete 3D map of the subsurface. So that, then why do we need this? I mean, I think it's self-explanatory, but just to give you some number, 30% of the cost from constructing offshore wind farms, 30% is going to foundation design. And if you mess up that foundation design, you're going to be costing a lot of money, basically. And this kind of imposes pressure to this industry partners to optimize this use of materials and avoid over-engineering of the structural parts. And when you look at the right-hand side of the image, this is a section of the geotechnical ground model, where you can see on the legend, it's the optimal foundation diameter and length. So based on this overall map, you can basically plan where to put your foundation when it comes to offshore foundation, which is quite big for us. This gives you an overall kind of like a summary of what geotechnical ground model is. You have the geophysics data, you have geotechnics data, you have geology, all this information, we combine it into one single map, and then that gives you the cost-optimized design. So this is normal practice in our company and in geotechnical engineering, but I mean, what's happening to lunar ground models, because we have very limited information on the moon. So what in the moon, unlike in the Earth, we have very limited material. We have very limited information in terms of laboratory testing. But I forgot to mention is that when it comes to geotechnical ground model, laboratory testing information is basically the crucial component to design your end structure. So when it comes to lunar soils, lunar engineering, I believe it is crucially important because you do a lot of scannings. I saw in your presentations, on your posters, that you do a lot of remote sensing, a lot of geophysics, testings and those probings, but you're missing the laboratory test data. And you need a link between the geotechnical test data and the mapping of what you did in terms of geophysics. So that's where the geotechnical ground model can come in. You can link the lab data and all the overall large-scale geophysical and remote sensing analysis and kind of get a better understanding of mapping of the lunar surface. So basically, the ground model are key tools for identifying and characterizing lunar resources when it comes to ISRU applications. And also, it's also very important for constructing your infrastructure on the ground, because in the end, you're going to be settling on the ground. Of course, the key designing for this infrastructure is, sorry, I'm a bit nervous, sorry. So it's basically important for your building structures, as I said, foundation, landing pads, anything you see out there, what you want to do there, all the utility lines, cables, pipelines, other surface infrastructures, and also when it comes to excavations, of course, I mean, you need to know the material, what you're doing, because you're building all these fancy machinery, but if you don't have the understanding of the ground, I mean, it could be quite hard to reach your end goal. And what we're missing is, so what are different from Earth to Moon is there's extreme environments that we don't encounter on Earth. So yeah, there's basically a lot to learn, a lot to discuss, and a lot to explore. So I'll just give you two examples of like what we're missing when it comes to lunar grounds. One from laboratory is, I repeat again, for design, laboratory testing is crucial. That's what you get all the main parameters. For instance, we get cohesion friction, which is a strength parameter when it comes to soil mechanics, and you have the stiffness that relates to serviceability. And also, when you go to the moon, I said the environment is different, stress state is different, everything is different. So we called it the advanced test, where you can measure soil properties under different situations or scenarios. And also, we can do some dynamic analysis in case you're interested in moonquakes. And for this, since a lunar industry is growing, we also, from geotechnical side, we're also interested, getting more and more interest on that. And there are a lot of diverse, institutions jumping into this field to test all kinds of materials, what we do, like in NGI. So the easiest way we do these testing is using lunar simulants, which is basically you have a mineralogy that corresponds to the moon, the lunar soil, and then the grain size distribution, which is, they say it's the same as the moon. But is it really the same? I can't really say. So I'm going to give an example of the thing called minimum and maximum density, which we measure semi-quantitatively in the lab. So maximum density, as its name implies, you can get in the laboratory without damaging the particles too much. Minimum density is the opposite. It's basically a loose state. And what you see here is, so on the graph, you see two simulants on the left-hand side, and the actual lunar soil on the right-hand side. Already you can see a huge discrepancy. And also not just the material itself, within the same simulant or same material, you can see a huge fluctuation of this density data. And why this is important? Because there's a thing called relative density. Relative density is basically an indication of how dense your material is. So if your material density is close to maximum density, so we call it the relative density is 100%. If it's minimum density, we call it 0%. And when you plot this, you can see there's maximum of 70% difference in relative density. This is not coming from material difference. This comes from different methodologies used by different institutions, which means if you use this, blindly use this information, this density data, that means you can get a variation of friction angle up to 15 degrees. What this means, to kind of make it easier, your landing pads has to be designed twice as larger if you have wrong data on this one. So it is crucially important, and it could be very dangerous if you get wrong information from this experimental site. And also another graph that tells you how different the material is. So the black dots and lines are from terrestrial material, which we call the simulants, and the red ones are from the lunar soil. So already there's a huge discrepancy just by the material itself. And then the second example is then called a cone penetration test. Cone penetration test is basically you jack in a cone and then measure the resistance to get strength of the material, strength of the ground, and etc. And in Earth, what our normal practice is basically we correlate this cone penetration data with the laboratory experimental data to kind of characterize the entire field of ground. But in the lunar surface, we don't have that, so we're developing a calibration chamber, which is part of a ESA-funded study, where we can vary we can vary pressure, temperature, and we make it X-ray transparent to see what's happening inside while doing the test. So to kind of summarize my presentation, so we need a standardization of the testing methods for lunar soils. It's critical because, if you want to have safe development of lunar infrastructure, you need it because it's not cheap. You can't repeat it as much as you want. And then if you want to have better utilization and better excavation method for these resources, you need basically a lunar ground model. And based on our study in NGI, we kind of identified two key challenges or path forward. We need systematic evaluation of lunar soil behavior, and we need more collaboration between communities. And we have a poster outside. Thank you.
Thank you very much, Taeheon, for that insightful presentation. We have a little bit of time, maybe one question, if we have it in the audience. Can I? Nobody? The presentation? I can't see. Can the mic please go to that direction? No. No problem. I think the presentation was so beautiful that nobody has any question. But I do have one for you. So how different do you think that these kind of ground models will be if you want to extrapolate it to other environments, like for Martian surface or maybe some other planetary body?
How different you mean?
Yeah, this is a lunar-based ground model that you're trying to achieve.
Yes.
If you want to extrapolate this for example, Martian surface, do you have any studies done for any other? For
Martians, not yet.
Okay.
But everything, the ground model and everything, it depends on the environmental conditions like temperature, pressure.
Exactly.
And also there's another variable from the sun. We don't have protection from the sun when it comes to moons. So all these variables change everything, so you can't really say what's going to be different or anything.
Okay, thank you. Thank you very much.
Thank you.
Yeah, you can go. Okay, so we move on to our next presenter, who is Francisco J. Guerrero-Gonzalez from Maana Electric, and he will be talking to us on developing beneficiation capabilities to support a future ISRU demonstration mission. Please join me in welcoming Francisco on stage. Do you want the mic? It will be switched on. once you come on stage. You can take it. Okay.
So hi everybody. It's probably usually for the regulars here at the Space Resources Week, just giving the usual presentation on Maana, an overview of ourselves and also the results from last year. But this year we wanted to switch it a bit around and basically go a bit deeper into one of the missions that we've been developing for the last 2 years, and also go a bit more in detail into the beneficiation part of Maana. But for those who don't know us, just a quick recap of who Maana is. So we are a Luxembourgish-based company founded in 2018. It's now 30 plus employees with the main focus on ISRU technologies and translating these ISRU technologies into producing space products, terrestrial products, mainly working on power systems. So our vision, and we are very happy to see that Blue Origin, big companies, Blada was talking about that yesterday, share the same vision of ultimately producing solar panels on the moon from lunar regolith. And one of these product lines that we have particularly for Earth, and it's the ground base for our space research too, it's the production of green silicon from low-value feedstock. So this low-value feedstock, it's mainly desert sand or mining tailings that we take, we beneficiate them in order to remove most of the iron, and then we put them into our metal extraction process, where we are able to extract metal silicon alloy. This metal silicon alloy goes further up following this ISRU paradigm into purification, where first we get metallurgical grade silicon, which is already variable by itself, but we are also able to further purify that into solar grade silicon, so 5M purity, and go into the production of green cells and further up into the production of solar panels here on Earth. So we have demonstrated already this process in the kilogram scale, and we are now going further into industrialization and commercialization in the order of hundreds of kilos and tons. And having this technology in mind, a couple of years ago, we were discussing with the stakeholders, but also internally between ourselves, we should start working on the same process, but for the moon, and that's how the source demo mission and the associated payload came to life, or it's coming to life actually. Similar approach, producing silicon and aluminum from lunar regolith using very similar technologies than the ones that we developed for Earth, but adapting those to the lunar environment. And the high-level mission objectives of SOURCE would be, of course, understand which are the resources that we can use to produce these metals, but also to demonstrate that our technologies work on those extreme environments. We defined ourselves also together with the stakeholders the first preliminary high-level requirements, which are producing 50 grams of oxygen and the equivalent amount of aluminum and silicon. And of course, operating for now only during the lunar days, so no lunar night survival capabilities. And something that is very important for us, it's being able to characterize the pre and post-processed regolith, but also the gas products in order to be able to really say that our technologies are working successfully. So here you can see a very high-level diagram of the payload architecture, where Maana's expertise relies mainly on the beneficiation and the reduction in order to extract these metals, and we are relying on partners to bring the regolith into the payload, which is also a significant challenge depending on where the payload is located within a lunar lander, or even if it's deployed to the lunar surface. And also we are relying on partners for the whole analytical unit that it's able to characterize, as I said, solid products, but also gas products. Today, we want to focus on the advances that we have made for the regolith beneficiation unit, the RBU, and then we will probably later this year share a similar presentation, but on the regolith reduction unit in a similar conference as this one. So we also had to define high-level requirements for the RVU. Those were mainly focusing on enriching the plagioclase mineral fraction of highlands regolith. Why highlands? Of course, it's more beneficial for us because it has a lower amount of iron, but also it's where all the moon missions are going towards the South Pole, where it's believed that highlands regolith it's most abundant. And the other high-level requirement was to process around half a kilo of regolith in 2-3 Earth days, so less than a quarter of a lunar day. When we started the design process, we saw 2 challenges. The first one was being able to miniaturize the technologies, the dry beneficiation technologies, and the second one was to select and be able to use a regolith simulant which was able to accurately replicate the magnetic properties, which wasn't apparently that difficult, but at the end it ended up on a really big nightmare, and it's still a nightmare. But for that, we first started testing also with our terrestrial background, what are the techniques that could work. Electrostatic beneficiation, we discarded it quickly, mainly because it was requiring large volumes, for example, for turbocharging. And we also saw that it had less potential for miniaturization, in the sense of power conversion, requiring large voltages that might not be compatible with other electrical subsystems that we have in the payload. So we focus more on magnetic beneficiation, where permanent magnets have a really low power consumption, and you can see there a couple of examples already from industry, from permanent magnet drum separators that have already been developed, are working. However, we still saw some issues on downscaling these drum separators, and we had to come up with a new design for the RVU, for the magnetic separator. This is the envelope of the breadboard that we are currently working with. You can see there the fact sheet. It's very low mass and very low power, which is what we were looking for mainly, to have it in a compact payload as source, which is in the order of 20 kilograms, but also as possibly a standalone payload where you only demonstrate beneficiation capabilities. So the second challenge, which was the lunar simulant selection, you have to think that the source of magnetism between terrestrial simulants and actual lunar regolith is significantly different. So just because of the oxidation state of iron, from iron 2 mainly in the lunar surface to iron 3 usually found here on Earth, that changes already the magnetic behavior, but also there's a huge contribution of nanophase iron on highlands regolith, or in general on lunar regolith, which also impacts a lot the performance of a magnetic separator, of course. So our first approach was to take a lot of different simulants and bulk simulants, so the ones that probably all of you are using for your own research. I'm trying to keep the same anorthosite to basalt ratio. You can see there either tubes or LHS or even the ones from off-planet research. And we observe a huge discrepancy between the magnetic behavior. We just took a handheld magnet and we saw how much we were able to recover. And if you check, for example, or you focus only on highlands regolith, you can see that LHS, you can recover around 30%, whereas for other highlands simulants, so the OPR simulants or even tubes, it's in between 70 or even 0, because it's mainly an orthosite. So this large discrepancy was an issue when selecting which one to test with. And also, of course, we have to know that none of these had nanophase iron implanted, so the behavior would still be different. Besides this discrepancy, we also investigated if particle size separation plays a role in mineral enrichment. In principle, we saw that for most similar, and also for the data that we got access from Apollo samples, It doesn't, so it's very uniform. However, we saw that for LHS, you could reduce a lot the iron content, which we use as a representative of the basaltic content, of course, by just sieving down to less than 200 microns. We guess that this is because the simulants or the similar components, so anorthosite and basalts, are grinded separately and then mixed instead of being mixed first and then grinded together, so that you have a way more homogeneous particle size distribution related to mineralogy. So because of this, and also because we observe a better performance of our RBU with lower grain sizes, we decided to work with below 200 micron fraction, and also we are already accepting that we are losing in between 30 and 20% of the regolith that is coming into the payload, but that's a trade-off that we did, and we believe it was worthy. So maybe here, just presenting finally the results that you can see. You can see in the plot both the enrichment ratio, which of course it's below 1 because we are not enriching, we are impoverishing the iron content, so we want to remove the iron content, so that's why the enrichment ratio is below 1. And you can see that just with one RBU pass, we were able to remove almost 50 to 60% of the iron, depending on the run and on the batch. And we also observed that we only needed one pass of the RBU, so we didn't have to design a very complex refitting system to have multiple passes, because the second pass of the RBU was more or less the same. We didn't see any enrichment. However, we saw a loss of yield, of course, where the non-magnetic fraction was going into the magnetic bin. And of course, we've talked about beneficiation for improving metal extraction, oxygen extraction, but this is just a simple use case on how beneficiation it's also relevant for infrastructure development on the moon. So here we produce 3 different glass samples, small glass samples, to check the transparency of those when changing the iron content. So you can see that the bulk LHS one, it's very dark. It's not fully black, but when you put it against a light, you can see a orange color. When you already remove the coarse fraction, because of this mineral enrichment happening in LHS, you already can see some transparency, although I'm not sure if it's super visible with the Maana logo behind. And in any case, once you pass it through our RBU, the transparency, it's already visible. You can see through. Of course, it still has a yellow color or yellowish color that should go more towards transparent once we improve and we optimize our setup by increasing the TRL. So just conclusions. So we were able to miniaturize this magnetic beneficiation separator, which is very important for us in order to keep within the budget and be able to fly something low weight. We know that euros per kilogram to the moon are not very low in the range. So that was a key requirement for us, and we also saw that we could remove a reasonable amount, that it's also helping our downstream processes in terms of purification of the metals afterwards. Still, the simulant, it's an issue, and we have to work internally, but also together with partners, to find a custom simular that it's really able to replicate lunar properties, lunar magnetism. And as I already mentioned, magnetic beneficiation, or in general beneficiation, is not only interesting for oxygen metal extraction, but also for multiple of other processes. And right now, we are mainly going into advancing the TRL, going into testing in vacuum, testing in high temperature to simulate the interfaces of the regolith beneficiation unit with the regolith reduction unit, and going into testing in low gravity. So with this, I want to conclude and maybe just a last remark, as we also, ESRIC was hiring, I think Blue Origin also opened a couple, or mentioned a couple of positions open. We also published a couple of positions last week because we are looking to reinforce our team. So if you are looking for a change, are willing to come to beautiful Luxembourg, take a look into the website or chat to me or to any of my colleagues and let us know about it. Thanks a lot.
Thank you very much, Francisco, for that excellent presentation. We are quite over time, but maybe one quick question. Yes, there is one. Can the mic please go there? Yeah. It's here. The mic?
No mic?
No mic. It's coming.
Yeah, a great presentation, Carl Hibbs from LSAI. Concerning the need for beneficiation and nanophase iron. As you know, nanophase iron is a small rind coating on grains that are generally unaltered, and orthocytic grains as well. How important is it that you remove nanophase iron? Because you may lose a lot of useful sample in that process.
That's true, and that's something that we are actually wondering. It's not necessary to remove nanophase iron, but the problem is more that if we have nanophase iron and we apply magnetic beneficiation, it's going to go out. So we don't want to remove it, but it's something that intrinsically happened because it's the main source of magnetism. So now we are wondering, and we had some discussions with colleagues last week on this, on if actual magnetic beneficiation is the way to go. We also don't think electrostatic beneficiation is the way to go, and these are the two main points, or the main two techniques when beneficiating. So it's still a question under debate, and I think that you can only test that with high fidelity simulants, or maybe even going to the moon to see if the performance that you expect it's the one that you get.
Thank you. Thank you very much, Francisco, once again. We'll now move on to our next presentation. We have Damian Pietrusiak from the Wroclaw University of Science and Technology, who will be presenting on conceptual design of separator for application in microgravity environment. Welcome, Damian.
Thank you for the introduction. Good morning, everybody. I'm here. I'm a representative of Wrocław University of Technology from Poland, and also there is a joint presentation. This topic is with the company 4Point. You may know them because they have also some things to do here in Luxembourg. So it's going to be quite in the same area that it was the presentation before. It is about the separator, but we are focused about the size beneficiation of regolith. So what's the actually genesis of this project? How it's come? Well, maybe I start first with this quote. It's from 2020, that size separation of bulk material in microgravity conditions is one of the most overlooked issue. And actually, for the last year and a half, I was involved in a project led by Astroport company in lunar landing site preparation, and to design, to make possible to build all of the pavements, all of the processes that are set that has to be done, all the 3D printing and that stuff. There is actually a question, well, yeah, we need regolith like this, like this, like this, yeah? We start with, let's say, assumption is that the razor, which is quite already known. Later on, we have some distribution of the raw regolith, but we have this point at which, okay, we want this part of regolith, we want this part of regolith, or this, and that is actually the issue which I quoted before. So here is an exemplary workflow of the regolith, and how we found ourselves in this situation. At first, actually, I've made quite, I believe, wide review about the size separation technologies in general on Earth, but also which are dedicated for space, because this is, for example, from the patent application from Colorado School of Mines, dedicated for regolith. This is some older patent for beneficiation in general on Earth. However, all the technologies we found in the team are cone-based or spiral-based for such a purpose. Yeah? So if we don't have a gravity or is the gravity low, so we can put the material to the cone, rotate, and it will be throughout, or we can put it to the cylindrical machine and use a spiral to move the material forward. Of course, we are rotating to have the material out. However, we were not satisfied fully with those solutions because I expect here problems, especially if we have no gravity at all. The cone probably will not work. And if we think about the regolith and its abrasiveness, when I think about the contact areas between spiral components and cylindrical components, it looks that there should be a lot of problems about wear, seizure, and whatever. And also, of course, we have to have at least 2 drives, more complicated mechanism. So, as I said, we did quite a big review, and it came up to our mind that we could actually integrate the spiral with the cone. So here's our idea that we have the same cone as previously, but we put a spiral which is integrated with the cone internally, and everything is rotating all together around. So in this case, if we put material here, without the spiral, the material will go through here quite fast. So there is a question about the performance of the machine. However, if we put also the spiral which is rotating, it will slightly counteract the force which is pushing the material through. So in that case, we can have, and of course the sidewalls are some sieving screens of the specific size we are interested in. So in that case, we'll be rotating, part of the materials will be through the sieving screen, and a larger part will be going through down on the spiral way. And here I put on the slide 3 main parameters to control the process from the mechanical point of view, which is the angle of angular velocity, cone angle, and spiral angle. So with that, we can adjust how fast the material will flow. And additionally, number 7 here is vibrating exciter, which will just move the sieving screen even more to increase the sieving performance. To give a more, I would say, visual idea for this, so in normal cone, let's say it's just simple cone, if we put the material, even if it rotates everything, we can assume that there is no relative motion, so the particle will go just right down, and only part of the small particles will throw away on the sieving screen. And if we add the spiral, which is, I want to underline, integrated, so everything spins around, so it's just one part. So the cone is pushing out the material, but the spiral is counteracting, so the particles are rotating around, and the path of this particle is much, much longer, so we have bigger, better performance of the sieving. On the main principle of that main idea, into our patent application, we put some exemplary designs of that sieving screens, of that impellers. That one you've already seen with such a rig. Here is a totally cone built totally by some kind of pathway. Here is, for example, cone with an imprinted pathway. Here is another more complicated design with already two rotating cones, but also on the spiral pathway integrated. And here's also another thing which is included in our patent application, in our idea that, of course, we want to have in one machine several size separation at once. That would be the perfect solution here. So from this concept point of view, we want to check if that's going to be working in the performance, because from the point of view of physics, of course, work, but from the design point of view, from the practical point of view, if we put a material here, so as on the first slide of the working principle, you've seen that the material is getting through the big size. However, the smaller size particles are going through another sieve, which is rotating with the same principle. So we are multiplying the idea here. So we have one sieving screen rotating, another sieving screen rotating, and another one, let's say it's from the theory, it's whatever big, but of course from the perspective of applications, not like that. So this is also the idea we have here. And slightly to make this vision maybe more ready to present, we've made these graphics. So again, we have the material input here, the rotating screen with the spiral pathway, sieving screen, and materials going through the opening down. Another idea with this sieving, with this size separation, because of course we are expecting the problems with the clogging of the sieving screens. So it is quite well-known idea in sieving screens that they are vibrating. However, they vibrate as a rigid body mode. So this is just one piece of material which is vibrating. But our idea is, and it's physically possible and it's technically possible, that we are going to make a structural design in this way that the flexibility vibration modes will be local. So I would say that the screen itself will be locally swept, let's say sine swept, just to get rid of the material, the particles which just got stuck in the openings. And of course, the idea is to combine those two vibration modes, I would say. So we have the rigid body modes, where the whole machine is, the whole sieving screen is vibrating, but additionally the sieving screen is vibrating locally, getting rid of the materials which got stuck in the openings. Well, here are some examples of the CAD design, which are really preliminary CAD design. And as I said, it starts at the Astroport project for the lunar landing site preparation, and as a result, here you can see the concept of the operation of such a sieving silo, which the technology is put into the inside of the machine. Just slightly we've made a super rough justification, so please don't stick to those numbers, but well, we checked. We have linear vibration screens on the Earth, very well known, and the average output is 280 kilograms per minute. For drum screen is much lower, but it's 14 kilograms per minute. But we checked, we found on this publication that the razor output, expected razor output, should be 100 tons per year. So actually, our machine with some factor of that it doesn't work 24 hours a day, every day. So actually, this machine should have the performance of 0.27 kilograms per minute. So we have a big distance of the I would say safety margin to overcome all the problems that we can face, for example, in space. And really short estimation what can be the power consumption here. But again, please do not stick to that number. This is just, we were checking on actually what level we are talking about. This is an idea here that the impeller is 1.5 meter, the average diameter is 1 meter, start time is 5 seconds, is made of aluminum, and we estimated that in that size there will be roughly 12 kilograms of regolith inside, so the power is 0.25 kilowatts. Well, what is going right now in this project? Right now, I'm combining the geometry with the discrete element method simulation already. It was said here a few words about this. So regolith simulant, I'm combining different types of particles shape to have actually working macro scale simulation, because we are interested in rather kilograms than grams of the output here. So I can't use particles like micrometers because it's going to blow up the simulation where the sieving screen is 1 meter high. Of course, I started with the physical testing on simulants in my laboratory. I check all the physical parameters to later on just to calibrate my simulation. And actually, I'm doing this with those 3 Highland simulants, 2 MER, 1 South Pole, and this is AGK Polish simulant. This is very, very starting simulation. It's not working, I would say. This is how it's going to operate in general, but this is more like checking at this moment the simulation is running well with the particles I've used. So it starts with that genesis, size separation. It's overlooked. But first, application on Earth. At this moment, we need to excavate even more difficult deposits with lower, material inside within it. That implies that there is the necessity to excavate more and more of that material and more processing, and processing is mostly water. That's what I already said, and actually we already know that the water is precious right now, and it's even in the Sustainable Development Goals of the United Nations regulation that till 2030 that should be dropped down the water usage. So we believe that this solution can first be applied on Earth. All of the small child, I would say, problems can be solved, and finally this technology can be used in space. Thank you.
Thank you so much, Damian, for that interesting presentation. We open the floor for questions. A quick one. Yeah, please. Mike.
Hi, thank you for your presentation. I'm Maarten Bruce Serut. I'm a planetary scientist. So I was just wondering, the sieving process, when you have the lunar regolith particles, which we know are very abrasive, which are very irregular on their edges, you have a lot of edges sticking out, would, even the shaking, when they get stuck in these little holes, would even the shaking be enough? And you might need another additional, loosening up method, so to say, to break those angles that get stuck in the holes. And how would you test that? Because I'm not sure whether on Earth we have particles that are that, irregular. So.
Yeah, thank you for the question. We are aware of this, and we, as I said, what I presented, this is quite really new idea. We have at this moment only simulations, but I believe we'll have to make those, of course, testing, and we will see how will this idea with this local resonating, local vibrating screens will perform, and at this moment we'll be able to judge if it is enough or not. We have another idea how we can clean the sieves, but it's not, I would say, patented yet. We'll see if that will require development of another things. I believe that with good mechanical base idea, we can probably with some partners build a sieving screen, which will also be using some magnetic field, maybe electrostatic field, and the combination of all the methods all together will give some sieving machine with the perfect performance. Yeah, maybe if there will be clogging, we will use some magnetic field that will remove the particles. But this is just my idea right now. I'm inventing. Yeah.
Thank you. Thank you so much once again, Damian. Our next presenter is Süleyman Salihler from Polimak Processes Technology, who would be discussing his work on advanced regolith conveying systems for harsh lunar and space environments. Please, Süleyman. Do you need this? Okay, go ahead.
Hello, everyone. Our main topic is today advanced regolith and space resources handling technologies that we have developed. Let's start by addressing the future missions that will require resource utilization. First of all, we will need so much resource, and we have to do some missions. For example, conveying large volumes of regolith or space resources for construction purposes, to build some space structures for lunar base or lunar landing pads. Also, we will need some sandbags to fill sandbags or regolith bags to, again, prepare some lunar bases. So we have to fill them, and we have to have some feedstock for them. Additionally, we need some continuous excavation or lunar regolith to produce oxygen, hydrogen, or other valuable resources. So we need to have some continuous excavation and transportation needs. Stockpiling of the regolith is also very important to have continuous feedstock. And after that, when humankind started to produce something from asteroids, we need to have some transportation, intergalactic logistics operations. So we have to fill some space-based containers to fill them, to transport the raw resources, and to utilize them even in any space station or Earth or another satellite or in another place. So to handle those kind of missions, we have to use some technology currently in use for a long time in the world, probably more than hundreds of years. So let's see which kind of technologies exist one by one and how we can integrate all them together. First of all, we have excavation and collection of raw resources. That can be used by using, excavators already known, or some devices on the moon, for example, NASA's Razor. I like that Razor design. It's a really brilliant idea. Also, we need to have transportation technology, for example, trucks on the Earth, but simpler trucks or robotic rovers on the moon. And we need conveying technology, conveying systems to horizontally or vertically move the material, convey the material, to, for example, fill a device on lunar lander to process the material, to analyze it. To have a feedstock, we need to have a stockpiling system. That stockpiling is generally done by filling the material and piling it up by a very simple manner. After that, we need to have a containerized transport or containerized temporary storage. In today's world, so many raw resources or materials or appliances are transported inside sea freight containers. Similar to them, we have to have some design suitable for low gravity and microgravity environment. And there are so many other types of bulk material handling systems, that including loading, filling, discharging, crushing, grinding, screening, sieving, weighing, and dosing. But to be able to handle those things, we need to address the challenges with regolith handling or other kind of space resources handling, such as abrasive nature, site and conveying route changes depending on your resource or reserve place location, temperature extremes, limited power supply in space environment, launch weight limitations, or low gravity again, static electricity, radiation, something like similar. Okay, what we did in Polimak. We are a 45-year-old company working in industrial processes, especially in bulk solids handling. So we are trying to shift some part of our business to space business. Again, focused on bulk solids handling, but now our bulk solid is space resource. First of all, the first solution is designing a container that can operate in microgravity or low gravity. In ordinary world applications, we have silos or tanks, depending on the handled material, either solid or liquid. We are filling a container from top by using gravity and discharging it again by using gravity. But if we do not have gravity, we have to have a different way of handling that material. In our design, we have an expandable and retractable type of silo that can pull the material inside itself, that can transport it together with the help of another transportation system, and again, it can discharge the material itself by pushing it outside. The other, our invention is a patent-pending modular drum conveyor concept, which I will explain in a few minutes, that is used to convey material from long distances, point A to point B, point A and B to point C and D. We can design it in any growth, any capacity, and any distance. The third one is using that modular drum concept on top of a Lunar Rover. So we can, again, transload the material, we can excavate the material, we can transfer it. The other one is a telescopic chute, which is already being used in world applications, especially in mining industry. When you are trying to have a stockpile, you will have so much amount of dust when you are discharging material from an elevated distance. So when it drops down, you will see so much dust. The telescopic chute is going down. All of the material is falling down inside the telescopic chute, and there is a skirt around that chute that prevents dust emission. When the stockpile is starting to raise, the stockpile loading chute is little bit moving up, and keeping the dust inside of it. So we are considering to use the same concept suitable for lunar environment to prevent dust emission on lunar construction works. After that, we want to integrate all of these concepts, also probably some other technologies altogether, to have an integrated space resources handling system that will solve several different missions. First of all, what is our first technology? As I said before, modular drum conveyor is very simple design, but very robust design. It is a patent-pending technology, and the main idea is it's having small, short pipes. And there are spiral flights inside of them attached to internal side of those pipes. And when you combine all of those pipes together and rotate those pipes, you can convey the material in low gravity environment. You can move the material horizontally and little bit inclined. But it is not suitable for vertical conveying, but we have some technology still on development to vertically convey the same material. And the most important part of it is that you can reconfigure this conveying line whenever you are needed. It can be assembled, disassembled, depending on your pathway. Its key features are modular design, suitable for installing excavators, lunar landers, yes, and also rovers. It is a fully contained system. There is no interaction between handled regolith with mechanical moving parts, such as electrical motors. And moreover, you do not have any big issue about abrasion. You know, regolith is very abrasive, but in this design, we are minimizing its effect due to the rolling effect of particles inside the rotating drum. In ordinary world, we are using, for example, augers or screw conveyors that are pushing the material inside the pipe. And there's a sliding effect that really causes abrasion. But in this concept, we are minimizing that effect. Of course, there will be so much amount of abrasion for sure, but it is trying to minimize that effect. Due to its simpler design, the rotating drums can also be produced by 3D printing or regolith. So we will only need to bring the electrical motor parts or some important components, but we can manufacture this design while using 3D printing. If we can integrate our modular drum conveyor together with lunar rovers, we can improve the operational efficiency. In ordinary mission concepts up to today, lunar rovers are very good machinery that can excavate, bring the material to a construction or processing site, and then coming back to empty to, again, collect the material themselves. So more than 50% of their operation is just coming empty. In this design, we are considering to use modular drum conveyor to transport the material for longer distances, but utilize the rovers in shorter distances. So we will have much more better operational efficiency. Okay, up to now, what we did in Polimak, we have designed and produced several different types, sizes, and capacities of modular drum conveyors, and tested them successfully. We have used plastics 3D modeling. We have used steel, stainless steel, different types of materials. And we can easily transport horizontally and inclined way. Also, we installed them on a rover that can move, that can excavate, but that can only collect the loose regolith, not the hard one, that can store the regolith temporarily inside and transport it. We have been still testing those systems in PTS space, Rostock, Germany. I also wanted to thank those guys that are helping us and develop the technology, and it will really help us to develop everything. So what we are aiming to do in the future and what we have achieved up to now, we have defined some real missions, how we can contribute those missions. First of them, as I said before, we want to use the lunar rover, not our rover. We are not a rover producer. If anyone is here producing rovers, please come to us, and we will be happy to use their rover. Use the rover, but install our lunar drum conveyor on top of that rover to collect material, to feed that material into our system, then prepare a feedstock by using our stockpile loading system. In second, let's say you have a lunar lander and there are so many devices on that lunar lander. Some kind of those devices may make some analysis, some of them may process the regolith, but they need to have the regolith feeding to them. So either you have to move those devices on the surface of the moon, or you have to bring that material on the lunar lander. So we are aiming to install that system on the lunar lander that can collect the material from the ground level and distribute it to several devices on the same lunar lander. You can take the material just by using the conveyor, or you can bring the material by using the rover, bringing it too close to the lunar lander and feeding the device again. Another concept is using several rovers as a swarm robotic system that can transport the material whenever needed and wherever needed. No need to install so many different devices, supports, anything. You only need the rovers. The other thing is sieving and mixing of regolith that can separate different particle sizes, or mixing them with anything, depending on the application. The other technology demonstration will be using regolith itself to produce 3D model of those drums. So we will be able to reach a sustainable lunar presence. After that, we are aiming to fill sandbags or regolith bags with regolith using our system and to prepare a good lunar base, lunar building. And nowadays, there is a good interest in inflatable structures. The main idea is pushing some gas inside of it, pressurized gas, and to keep that good shape with some amount of strength. But if we will be able to fill those inflatable structures with regolith, then we will have a very good shield. So we are aiming to use this technology to first fill inflatable structures and then fill the regolith inside of those structures. After all, for the long term, we are aiming to develop the transportation container for microgravity environment. And another design of this container will be suitable for enclosed, containerized, temporary storage on lunar base production. After that, as we are a bulk solid standing company, we are still developing several different technologies for conveying any kind of powdered and granular material. We are still developing similar systems and different systems, and they are trying to be used inside of any kind of international and intergalactic projects. Now we are actively engaging with several companies, and you can see our technology just after this tour. We put the small model of our rover and the conveying system. That's all for the time being. Thank you.
Thank you so much, Süleyman, for that thought-provoking presentation. The floor is open for questions. Anyone? Okay.
I guess I have answered everything.
I know, everybody understood everything.
Thank you so much.
I do have, oh, there's one question actually coming from there. Okay.
I like your presentation. Just a really quick question. You showed some pictures of some preliminary experiments that you did with your model here on Earth, and I saw that all the motor drives had like passive cooling systems on them, like some cooling fins and things like that. But I guess on the moon, how are you planning to, do your heat transfer from your motors?
Yes, very good question. Now we are developing the conveying technology. Of course, there will be several systems connected to that. Electrical motors are still being used in widely used industrial motors, not space grade. And you are right, we have to find a solution to cool or sometimes to heat up the motors.
Thank you.
Okay.
Okay, thank you. Looking at the time, I have a question, but I'll ask you later on, and we would move on with our session. Thank you so much, Süleyman, once again. Yeah, thank you. So moving on. That's a great audience. Moving on, our next presentation is going to be online. We have Kate Smith from the University of Manchester, who will be talking to us about towards development of low-gravity ISRU excavation methods using discrete element method simulations. Over to you, Kate.
Okay, good morning. And sorry, everyone, I couldn't be there in person, but thank you for Vibha and the team for accommodating me. So here in Manchester, we're very interested in looking at the excavation methods and how we actually get the regolith to our processing plant. So sorry, I think I have to say next slide. Yeah. So we already know there are various different processes that have different requirements in terms of their feedstock. But all of these processes have one thing in common, which is, if we go next slide and next slide, yeah, which is the beneficiation process. So in some way, we need to improve the feedstock to tailor it for whatever process is coming next in the ISRU chain. If we go next slide, I think we know that different processes require different levels of size separation. So the previous speakers have talked about this size separation. And that certainly the tests that we are currently doing only use certain size fractions on Earth. So any tests that we've done on these different ISRU processes we very carefully select what size we have for our feedstock. But how are we going to do this on the moon? So if we go to the next slide. Yeah, how are we actually going to achieve this? If we look at the overall ISRU process chain, we have various aspects. We have the waste side, the handling, and then some level of characterization to make sure our feedstock that's coming into the process is appropriate. So at the first instance, we've always got to have some sort of excavation. We need to extract that regolith from the lunar surface. And then we need to, if we go next slide, we need to do some sort of handling, some sort of characterization, and then that goes into our beneficiation step. So those are the first two essential parts of any ISRU process chain. And then once we've done the beneficiation, we're obviously, if we go next slide, going to produce some waste. And then we will get if we go next slide, improved feedstock. So we'll do the handling and we'll do some characterization to make sure that feedstock is appropriate for our process. So next slide again, yeah, so we go into processing. And finally, if we do next slide, we will get into we'll have another form of waste from that processing. And then finally, we will get our product. If we go next slide. Yep, so we will get our product, which could be materials or oxygen or some sort of building construction. But if we go next slide, I think, yeah, without excavation or beneficiation, none of these ISRU processes are possible. So sorry, excavation and beneficiation, if I highlighted there, these are generally considered as separate process steps. I think some of our previous speakers have talked about systems that work together. And that's something that we are also looking at, how we can combine the excavation and beneficiation step initially to reduce that initial handling step and that initial characterization step so we can improve efficiency on all of these processes. So in light of that, we are looking at a design, so a basic prototype that we've been looking at, which includes three key components. So we have a base, which allows our mechanical arm to move around. We have the arm part, which we can move that arm, and then the excavator, the initial kind of excavation or inlet side. And so this tool allows us, if we go next slide, to have some sort of two-stage separation. So we can separate our regolith into two different size fractions, coarse and a fines, to be able to then feed the next process on. And if we go next slide, we can see just here a diagram of how this excavating scoop that will allow us to excavate the loose regolith on the lunar surface will have an initial step where it will move forward and then it will go upright. In that process, we'll have hopefully the lunar gravity will allow some level of separation through the sieving system, but we also have an integrated vibration mechanism which will allow some deblinding of the sieves and also promote that size separation through those mechanisms. And then we have these little trapdoors that will allow the separated material to go into one channel or another. So we then have some level of beneficiation in this. So in order to sort of test this process, if we go on to the next slide, I think, hopefully, yeah. We need some sort of mechanical analog, so an analog for the regolith that will behave in a mechanical way. So we're not looking at this stage at sort of chemical analogs. We're really looking at how does that regolith analog behave mechanically with our system. So we need to reproduce the size of that regolith. So we have we've characterized the analog that we have found that's suitable. And we have a similar sort of size fraction to lunar regolith. We also need to look at geometry. So we've done some SEM analysis to see if the geometry is sort of relevant. And we've done some physical testing, so on the material properties. So if you go next slide, I think it should bring that up. Yeah, to look at the angle of repose to see if this is similar. So if the material properties are behaving in a similar way. to lunar regolith, so that we can use this to test our system mechanically. So if we go next slide, I think we've got some video here. Hopefully that's playing for you nicely. It's playing on my screen, so I hope it's playing on yours. Of the testing excavator with you can see the green little box on the side, which is the integrated vibrator, and then on the right-hand side of the screen, you can see where we've integrated, or on the left-hand side, integrated that into our test rover. So the next stage we wanted to do is do some low gravity testing, but as we all know, it's quite challenging to emulate the low gravity environment here on Earth, and particularly with particulate matter, it's integrating that into any sort of physical test system is also very challenging. So if we go next slide, I think, yep. So that's just the kind of indicating particulate matter is quite a challenging thing to do in low gravity testing. So if we go next slide, I think, yeah. We considered drop towers, but obviously the volume for the drop tower testing is quite small, and also the time that you have for actual low gravity conditions is quite limited. So the next consideration we looked at were parabolic flights, where you can get about 20 seconds per parabola. And we have some previous experience with other experiments that we've done, not on the excavation side, but on oxygen extraction methods. So if you go next slide, you'll see some of our team members, previous team members here with a rig. You can see the rig is a little bit bigger than maybe you would get in a drop tower, so it could accommodate potentially excavation tool and excavation system. But there are challenges again with the particulate matter and making sure that everything is settled before you do your tests and everything is in the right condition. And then the final option could be sounding rockets, but again, it's very, very volume constrained, but you have potentially quite a long period, 12 minutes of low G conditions or zero G in some cases. So all of these could be options, but in order to do sort of more rapid prototyping and testing, we're looking at, if you go next slide, how we might do some of this testing initially with simulation. So I think previous talkers have spoken about the discrete element method. And so this is what we've been looking at. So in discrete element method, you can, if you go next slide, you have different contact models. So the hard sphere model is considering these impulsive collisions, and it's okay for binary collisions or things where you've not got other interparticle forces. But what we need to consider are the electrostatic effects and the gravitational effects, and any sort of other interparticle forces that we need to accommodate. So the models that we've been looking at are using, if we go next slide, I think it should come up, yeah. There's the soft sphere type model where it allows, it's non-impulsive, it allows some sort of particle overlap, and the overlap is proportional to those interparticle forces. So we can start to look at accommodating electrostatic effects and gravitational effects within our models. So if we go next slide, I think, yeah. So we've done some calibration of our model, and we in order to do this, we looked at some material properties. So again, we went back to looking at the angle of repose. So in our DEM simulation, you can see it compares very well to our experimental angle. So we have an angle of about 40 degrees in the DEM, and also the same in the experiment. And we also looked at how we might scale. So I think one of the other speakers mentioned the challenge of if you've got lots of particles and small particles as well, that's going to pose a significant challenge in trying to upscale these. So you can actually use pseudo-particles where you have a number of particles that are representing a group of particles that can look at the sort of scaling factor. So we can actually reduce the number of particles in our simulation frame, and we can see we still get sort of relatively reasonable response in terms of our results, in terms of that simulation of the angle of repose. So I think we're fairly kind of happy in that respect, but we do need to do some more testing around that to just make sure that it is kind of accurately portraying all of the interparticle forces as well. So if we go next slide, I think, yeah. So just summarizing the comparisons that we've done a basic experimental physical test that we have an excavator, which we have put in our on top of our lunar regular sandpit. At this point, it's just being actuated by an arm which is pushing it. And we've used a similar geometry within our physical testing and our simulation campaign. And we can see, if we go to the next slide, some of the results there. We have the excavation forces, both from in the blue line, so I can't see very well on the slides. Checking through, yeah, it's so in the blue line we have our, if we go back one slide, sorry. Yeah, in the blue line there, you can, the blue dots, you can see our discrete element method simulation, and then the red dots there, you can see our experiment. Both of the simulation and the experiment are obviously done under Earth gravitational conditions, but we can see that they kind of line up very well. So at least it's capturing the physical properties and the forces that we're experiencing on our excavator. So we can kind of have some confidence with the method in that respect. So I think just in the next slide, I think the final thing to say is the next steps are to sort of do more of the physical testing and a more representative simulation of our actual excavator arm design, and then potentially do some low G validation, but also look at how we, in our simulation, what the effects are when we change the gravitational effects or change the electrostatic conditions, and see how that influences the performance in the system design. So I think the next slide, I think that brings us quite neatly onto the end. So if you have any questions or anything further, otherwise I'd like to thank you for your attention.
Thank you very much, Kate, for that. It was a very nice presentation. However, as it's an online talk, we are not taking questions here, but you can always contact Kate directly and have a more engaging discussion. Thank you, Kate. Thank you once again.
Yeah.
Moving on, we have come to the final presentation of this session. And for that, we have Stephen Kay from GMV, who will be talking to us about locomotion for ISRU activities, the case of the European Moon Rover system. Stephen, the floor is yours. Please.
Hello, good morning, everyone. So my name's Stephen Kay from GMV. I'm presenting this on behalf of a colleague of mine from GMV Spain called Cristina Luna, who could not be here today, unfortunately. So as mentioned, I'm going to be talking about a slightly different topic for this morning, which is on the locomotion side of ISRU, and specifically the European Moon Rover system. So what I'd like to do is talk a little bit about the project overall as an introduction, and then I'll present the baseline design for the system that we have, including in particular the locomotion concept for the vehicle. Then moving on to the test campaign and some results, and we'll finish with some nice videos of the test campaign as well at the end. Okay, so the European Moon Rover system is in pre-phase A study. It's a funded activity by the European Space Agency. GMV are one of the two prime contractors bidding for the mission. In concept, the EMRS at pre-phase A level is effectively to investigate the requirements of the rover, taking into account the 4 missions which are coming out of the Argonaut study. So the Polar Explorer, which is looking for, it's targeting a scientific exploration of the South Pole region of the Moon. We also have the ISRU plant, where the rover will deliver the regolith to the plant. We have the Lunar Gem, which is another exploration case, but targeting the equatorial near side region, and the ALO, or the Astrophysics Lunar Observatory, which is a far side mission for construction of a telescope. What's key in the definition of the rover system overall is that it is highly modular, the idea being that we can have one rover concept with minimal configurational changes for multiple missions. And to do this, it must carry out many different tasks across these missions, so including excavation, handling the scientific payloads, deploying these payloads using manipulators, and also performing assembly tasks in construction. Here you can see a couple of examples of it, including with a mock-up of an excavator that we'll talk about a little bit later on as well. So in terms of the baseline rover design, our constraints are really coming from the Argonaut's lander. So when the rover is stowed on the lander, it's around about 1.5 by, 1.5 by 1.5 meters envelope and about 0.7 meters tall, not including any top payload. When it's deployed, it extends to about 2.4 by 1.5 meters when the wheels turn round and it's in its deployed configuration, raising to a height of around 1 meter for operations. With the rover, we have a ground clearance of around up to 0.3 meters. However, this is configurable using an active suspension setup that we'll cover in the next slide. Overall, the rover is four-wheel configuration and is able to be highly modularized depending on the mission that we're targeting. So in concept here, what we use is the central bay of the rover is hosting the rover avionics, and then the side bays, the top, and the front and back are reserved for mission-specific payloads, scientific instrumentation, or anything else that the rover must carry. So talking a little bit more about the locomotion concept, there's three main characteristics to discuss here. The first being the wheels, the second being the steering concept, and third is the active suspension. So the wheel concept we have for the rover is a variable stiffness wheel. So this allows us to effectively deflate or inflate, in quotes, the wheel in different lunar regolith conditions using a mechanical spring stiffness adjustment mechanism on board the wheel. We also have an offset steering configuration as opposed to the typical on-top steering configuration that you might see for these types of lunar rovers. This really allows us to optimize the integration of the rover inside the available volume of the lander, while also allowing us to host the maximum amount of payload for the missions as well. And then lastly, we have an active suspension system, which comprises a set of motors and which allows us to independently control each of the wheels of the rover. We also have a passive mode, and then we also have a mode where we can absorb energy during the traverse using the motors in sort of an impedance mode as well, potentially. Overall, we have 4 locomotion primitives where we're able to drive in a conventional sort of point turn mode where we turn the wheels to form a circle, and then we can rotate around the center point of the rover. We also have a crab turn mode, which is a bit unconventional, but effectively allows us to rotate the wheels all facing in one direction and then traverse in that vector. We also have a dual Ackermann mode, which is similar to the way your car will navigate, allowing us to form complex splines or complex curves for traversing. And then lastly, we have quite the straightforward skid steering approach, where we turn the wheels in opposite directions to turn on the spot. In terms of test campaign, we performed quite an extensive test campaign in the DLR facility in Munich, which you can see on the right in the soil test bed there with Lunar Simulant, and then also the GMV planetary yard in Madrid, Spain as well, called SPOT. These tests really were focusing on the locomotion system overall, and we put the rover through its paces in terms of slope conditions, so up to 25-degree slopes at different velocities, and all the different locomotion modes that we had present on board the rover. Also, uneven terrain traverses as well, so not just flattened, compacted soil, and then also the ability for the rover to overcome obstacles, both single, double, and sort of variable size, variable shape obstacles. And then lastly, we performed a number of tests using the excavator mock-up that we have as well for the ISRU case. So looking quickly at some of the results, one of the areas we were really interested in was the wheel deflection. So Using some image processing, we were able to establish the impact that the rover geometry and the locomotion system had on wheel deflection as the rover was driving in various conditions. What we found was that effectively we had quite a minimal impact of deflection on the locomotion system, or the locomotion system had to the wheel deflection, with around 3.5 to 5% deflection found. Overall, this configuration was found to be satisfying the requirements that were derived at the start of the activity, and in all the different weight configurations that we tested during the activity too. Okay, so looking more at the traversability results, what we found overall was that the rover is very well suited in long traverse or in quite complex terrain environments, where we're traversing up and down obstacles and over slope conditions. However, in something like an ISRU condition, this is one of the areas of configurability that we could address in future for where we're driving perhaps in less distance, and then we can optimize the locomotion system to account for that. Also, we found the system to be very functional when we were dealing with tractive cases as well, so like with the excavator. Looking quickly at some of the analysis, we found, first of all, we evaluated the angular speed efficiency, which gives us an estimate of basically the energy that the rover has to use to make a point turn in two of the more conventional cases. So the point turn mode where we turn the wheels and then rotate, and also the conventional skid steering motion as well. Overall, we found that this was satisfactory to the requirements, and that the locomotion system overall was quite robust in this case. This is quite important to have a high efficiency here, because when the rover is turning, obviously it's subjected to the forces and the characteristics of the regolith that it's in. So therefore, you could run into issues of rover safety or digging yourself in should the efficiency not be particularly good in this regard. We evaluate also the same test, but in terms of energy consumption, where we see here the expected result being that the point turn mode becomes much more efficient than skid steering due to the characteristics of the way that the wheels move in the soil. So what we see initially at the start is an initial spike of the point turn energy being used, which is indicative of the steering motors turning the wheels to start initiating the point turn. And then very quickly, at about 76 degrees, we see the efficiency switch over, and we find that the point turn mode is much more efficient than skid steering as expected. We can evaluate this in a slightly different way in terms of what we call the cost of transport, which is effectively a metric of how much energy the rover requires to make the traverse. What we've done here is evaluate it in terms of the slope angle, or the degrees of slope, where we take effectively the power divided by the linear momentum and the gravity, and it gives us this von Karman curve, where we can see that effectively the wheels in the locomotion system overall are performing better on the higher slopes that we're driving on, which again is important for these sorts of missions that we're studying the rover for. Now lastly, we've taken a plot of the odometry that we recorded from the rover on board and the commands that we give to the rover, as well as the ground truth data we recorded in the facility using motion capture. And with this, we can overlay the commanded versus the executed results, and we can see that overall in all conditions, so for Ackermann, nominal straight line traverse, crab, and point turn, we're able to effectively execute those commands in essentially what is an open loop condition right now for us, meaning that there is no guidance navigation control stack running on top of these tests. So with that, I'd like to now share a video, if it will work, on the test campaign performed. that, I'd like to finish, and thank you for your time for listening.
Thank you so much. I'm sorry that we don't have any time for questions because we're running over time, and I've got some important information. Number one, it's the coffee break, but number two, we are going to have a photo in the coffee break with the people from UNOSA. So it's just going to be outside there. And finally, we will recommence at precisely 11:10. And I would love to invite you all to be seated by 11:10 because we'll have Catherine Corner from NASA, and she needs to start precisely on time. She's already moving it by 10 minutes for us. Thank you very much. So photo first.